Hi everyone, welcome. This is Bill. Today we will study linear algebra together. It will cover the content of chapter 2 of Deep Learning book. Firstly, let's have a look at the outline of the part 1. You know this part is about some applied math and machine learning basics. It will cover 4 fields: linear algebra, probability and information theory, numerical computation, and machine learning basics. These are, and in this part, you will learn some very basic math that is highly relevant to deep learning and machine learning. And also you will get some very core idea of machine learning basics, which is, I think, is also very important for our further study of deep learning. So linear algebra is an extremely powerful and elegant piece of mathematics. It's widely used throughout science and engineering. A good understanding of linear algebra is essential for understanding the deep learning. And I think, but this chapter is not a very comprehensive survey of all of linear algebra. It will focus on the subset that is most relevant to deep learning. So if you have no exposure to linear algebra at all, this chapter will teach you enough knowledge to read this book. But it is highly recommended to consult another resource focused exclusively on teaching linear algebra. I have listed some very great resources on the reference slide. You can find some very great courses in that slide. So the first thing we learn linear algebra is to get familiar with some basic building blocks, and also we can get familiar with some notations. The first concept is scalar. Scalar is a single number. It can be an integer, real number, rational numbers, or other types. So in this book, we denote scalar in italics, and we like to give scalars lowercase variable names. And when we introduce scalars, we usually need to declare what kind of scalar it is. We can do it like this. So by this way, we declare a new scalar named x, and the type of x is a real number. We use this note to denote the set of real numbers. And the second one represents a natural number n. A vector is an array of numbers. It's a one-dimensional array of numbers. And in a vector, the numbers are arranged in order. And therefore, we can access each element in the vector by its index in the ordering. Typically, we like to give vectors lowercase names written in bold typeface. So in this way, we declare real vectors with the size of the vector is n. Sometimes we need to explicitly identify the elements of the numbers. So then we write them as a column enclosed in square brackets, like this. So in most contexts, we will represent a vector as a column, not a row. A matrix is a two-dimensional array of numbers, and each element is identified by two indices instead of just one. And we usually give matrices uppercase variable names with bold typeface. And when we need to explicitly identify the elements of a matrix, we write them as a array enclosed in square brackets, like this. So this represents a 2 times 2 matrix, and with the number of rows is equal to 2, and the number of columns is equal to 2. So when we want to identify the elements in a matrix, we will use this kind of note. This means therefore A21 represents the element in the second row and the first column. Tensors represent arrays with more than 2 axes. But in general, a tensor can be also regarded as an abstract concept. And in this way, a vector and the matrix are just special cases of tensors. So you say if the tensor is one dimension, it becomes a vector. If it's two-dimensional, it becomes a matrix. And it can have more than 2 dimensions. But if the tensor is the dimension of tensors is larger than 2, it becomes very abstract and very hard to imagine. The first operation of matrix we study is the matrix transpose. It's a very important operation, and we can just denote it in this notation. So after transpose, the element of index ig is equal to the element of index ji of the original matrix. The transpose of the matrix can also be thought of as a mirror image across the main diagonal. The main diagonal is the line starting from the left upper corner and running down to the right, the most right and down corner. So this line is the main diagonal of this matrix. These are some other matrix operations. The first one is about adding matrices. So if we want to add matrices, we must guarantee that the matrices has the same shape, and then we can perform the adding operations by add their corresponding elements. We can also add a scalar to a matrix or multiply a matrix by a scalar just by performing that operation on each element of the matrix. Adding a vector to a matrix is not a very conventional notation, but then it may occur in the context of machine learning and deep learning. People in this field tend to use this notation to get a concise expression. So in this operation, a vector is added to each row of the matrix. Matrix production is one of the most important operations of matrix. In these operations, when we multiply matrix A and B, we will get a new matrix named C. And the element of the matrix C is determined by this expression. It seems very complicated, but let's look at this figure. So this is a matrix C. This is A times B. So if we want to get the element of this element in matrix C, we need to do a vector product of the row vector in this row and the column vector of this column. So in this way, we can think of the matrix product as computing Cij as the dot product between the row, the ith row of a matrix A and the jth column of matrix B. So it's noted that the product of two matrices is not just a matrix containing the product of the individual elements. It's not we cannot just do the element multiplication by the corresponding elements. Such an element actually exists, and it's called the element-wise product. But in this matrix product, it's a very different operation. So in this matrix product operations, we must guarantee that the number of columns of A is equal to the number of rows in B. Otherwise, we cannot do the matrix product between two matrices. Here are some properties of matrix product. It's distributive and associative, but it's not commutative. It means usually AB is not equal to BA. It's not a commutative operation. Okay, now we know enough linear algebra notation and definition, so we can write down a system of linear equations like this. In these expressions, A is a known matrix, B is a known vector, and X is an unknown vector that we want to solve. So you see this is a matrix vector product. And if we expand these equations, we can get a series of expressions. Every expression is a vector and vector product. So you see this is actually a very elegant and concise notation of our linear system. So the linear system is a very core problem in linear algebra, and many concepts and theories are just centered around it. To solve this problem, we will have three conditions. The first is there is no solution. The second is that there is many solutions, and the last is that there is exactly one solution. So I will talk about this condition next. So this condition means that the multiplication of the matrix is an invertible function. It's invertible. So based on this, we can get an operation of matrix inverse. But before we get to matrix inverse, we first need to define the concept of an identity matrix. So the structure of the identity matrix is very simple, and it's all of the entries along the main diagonal are 1, where all of the other entries are 0. So this figure shows the 3 times 3 identity matrix. So we usually use I to denote an identity matrix, and also an identity matrix it must be a square matrix. So we use I3 to denote this identity matrix. In general, if the shape of the identity matrix is n times n, we can denote it as In. So one very strong property of identity matrix is that it does not change any vector when we multiply that vector by an identity matrix. Matrix inversion. The inverse of a matrix is that when we multiply it with its original matrix, we just get an identity matrix. And the inverse of matrix is just denoted as this. I think it's very similar to the concept of the reciprocal of a real number. We say in the matrix theory, there isn't a divide operation like this. It doesn't exist. But we can use the matrix inverse as a substitute. We can do this thing. So if we have this tool of the matrix inverse, we can solve a linear system following these steps. First, you see, this is the original expression, AX is equal to B. And first, we just multiply the matrix inverse of A on both sides, and then we finally will get this solution. So this is a very good, it seems a very simple and elegant solution. But unfortunately, most practical software doesn't perform in this way, because the matrix inverse can be represented with only limited precision on digital computer. It means that the computation of the matrix inverse is not very cheap. And so in real software, we use another algorithm to solve this linear equation system. But this matrix inversion is very useful and very important for doing some abstract analysis. Now let's look at the system of linear equations in another view. You see, in the matrix of A, each column of the matrix A is actually a vector. We can think of it as different directions from the origin. So imagine there's a space, then the columns of A just define different directions from the origin. It means that there are different vectors from origins, which is described in A, and therefore the matrix vector product can be expressed in this way. This notation is linear combination. So in general, a linear combination is defined like this: given a set of vectors from V1 to Vn, a linear combination is defined by multiplying each vector by a corresponding scalar coefficient, and then summing up the results. So by this way, we can get a lot of points in the space that is described in the columns of A. And the set of points, which is the set of results of linear combinations, is called the span of a vector, span of a set of vectors. And so in this way, let's look at this equation again. So the left side is actually a linear combination of the columns of A. So to solve this problem becomes another problem. That is, we want to know if the vector B can be described as a linear combination of the columns of A. So in this way, whether the equation has a solution also means that whether B is in the span of the columns of A. So the span of the columns of A is also named as the column space or the range of A. These are two concepts. One, we have a set of vectors. It's linearly dependent if at least one of the vectors in the set can be defined as a linear combination of the others. It means that we can find a vector in this set that can be defined as a linear combination of the others. Then this set of vectors is linearly dependent. Otherwise, if no vector in the set can be written in this way, then the vectors are said to be linearly independent. Now with the new concept and tools, we understand that the matrix vector product AX is actually a linear combination of the column vectors in the matrix A. And it also represents a point in the column space of the matrix. Therefore, if we want this equation to have a solution for all values of B, we should guarantee that the column space of the matrix encompasses all of Rm space. These conditions also mean that the matrix should contain at least one set of m linearly independent columns. Otherwise, we can find B that cannot be represented by the linear combination of the column vectors. So this condition also indicates that the number of columns should be larger than or equal to m. Okay. Now, do you remember the matrix inverse? Do you remember the matrix inverse steps to solve these equations? So if the matrix is invertible, which means that if the A minus 1 exists, we can just find the solutions by this expression. You see that if the matrix is invertible, we can find only one solution for each B. So to achieve that, firstly, the matrix should be a square matrix. It means that n should be equal to m. Otherwise, there will be more than one way of parameterizing each solution if n is larger than m. And the second condition to achieve this is that all of the columns must be linearly independent. This is because if we want the equation to have a solution for any value of b, we should make sure that the matrix have at least one set of m linearly independent columns. And now the number of columns is just equal to m. So we should make sure that all of the columns be linearly independent. So that's the two conditions that we can guarantee the matrix is invertible. So another concept is the singular matrix. It represents a square matrix, but with linearly dependent columns. So if A is not a square matrix, or A is square but singular, it doesn't mean that there is no solution for these equations. It can still be possible to find the solutions to solve the equations, but we cannot use the method of matrix inverse to find the solution. Okay, maybe you'll find this theories or definition a little difficult to understanding, and that's very common. It's actually very abstract, very tough and confusing to understand at first. If you want to understand it better, you should go to find some examples or find the proof behind the theory. But this chapter is only a very rough and quick review of the basic ideas of the linear algebra. We just need to get some insight and get a little familiar with the concept and definition of linear algebra. It doesn't matter if you don't understand some of them. We can also continue our learning with this book. So let's go on. Sometimes we want to measure the set of vectors, then we need to use norms. So norms are functions that measure the set of vectors. It's very intuitively similar to the distance from the origin to the point represented by the vector. So, but in a more abstract way, norms can be any functions that satisfy these three conditions. First, fx should be equal to 0. First that if fx is equal to 0, we can say that x is equal to a zero vector. And the second condition is the triangle inequality condition. And the last condition is that if f alpha is a scalar, So f alpha x is equal to the absolute of alpha multiply fx. So if a function satisfies these three conditions, we can use it as a definition of a norm. Here is an example, and it's the most widely used norm, which we call the LP norm. This is its definition. So in this definition, P should be greater or equal than 1. Should be greater, and P should be greater than or equal to 1. And also P must be a real number. So when P is equal to 1, when P is equal to 2, it becomes the most popular norm, L2 norm. The L2 norm is also known as the Euclidean norm. It is simply the Euclidean distance from the origin to the point identified by x. When P equals 1, it becomes L1 norm. The L1 norm is also very commonly used in machine learning when the difference between 0 and non-zero elements is very important. Because L1 norm usually encourages the parameters of the model to be very sparse and to have more zero elements. This property can sometimes make the model more stronger and more robust. Another norm that commonly arises in machine learning is the max norm. And in this norm, it simplifies to the absolute value of the element with the largest magnitude in the vector. So sometimes we want to get the norm of matrix. So this is the most commonly used. Its name is Frobenius norm, and this is its expression. And this expression basically has the same ideas with the L2 norm or so-called Euclidean norm. So next we will get familiar with some very special matrix and vectors. And these matrix and vectors are very particularly useful in the machine learning. The first one is the diagonal matrices. The diagonal matrices consist mostly of zeros and have non-zero entries only along the main diagonal. We have already seen one example of our diagonal matrix, which is the identity matrix. And this is a very strict definition of the diagonal matrices. It means that in these matrices, we only have non-zero entries along the diagonal line. So if L2 norm of a vector is equal to 1, then this vector is said to be a unit vector. A symmetric matrix is that the transpose of the matrix is just itself. So when we say two vectors are orthogonal, it means that their dot product equals 0. If the vectors are also unit vectors, we then call them orthonormal vectors. So in an orthogonal matrix, all of the rows of the matrix are mutually orthonormal, and all the columns are mutually orthonormal too. So this orthonormal matrix has a very interesting feature that its inverse it's just its transpose. So it becomes very cheap to get the inversion of a orthogonal matrix. It's very interesting. Okay, now we get to another big part of linear algebra, which is eigendecomposition. We need to do the stuff of matrix decomposition when we want to do some analysis and get some more deep property of the matrix. And eigendecomposition is just the most widely used kind of matrix decomposition. So this definition is based on the square matrix. So at first we should make sure the matrix A is a square matrix. An eigenvector of a square matrix A is a non-zero vector V that multiply A and V alters only the scale of V. So here lambda is a scalar. So if a vector satisfies these expressions, it's the eigenvector of A, and the lambda is the eigenvalue. So for a matrix, it usually has more than one eigenvalues. If we can, after we get all of the eigenvalues and eigenvectors, we can do the eigendecomposition in this way. The expression means that the A can be decomposed by three factors. The first factor is the matrix V, which is composed of different eigenvectors of matrix A. And the second factor is a diagonal matrix composed of the eigenvalues of A. And the third factor is just the matrix inversion of V. So not every matrix can be decomposed into eigenvalues and eigenvectors. And in some cases, the decomposition exists, but may involve complex rather than real numbers, which is not a very good thing. But fortunately, in this book, we usually decompose only a specific class of matrices that have some very simple decomposition. Specifically, every real symmetric matrix has a real orthogonal engine decomposition, like this. In this function, Q is an orthogonal matrix. You know, orthogonal matrix, it has pretty good properties, and the last factor is the transpose of the orthogonal matrix, which also equals to the inversion of the orthogonal matrix. Eigendecomposition is very useful. So this figure just shows some effect of eigenvalues. So here in this figure, we have a matrix A, and it has two eigenvector, V1, V2, with corresponding eigenvalues denoted as number 1, number 2. So in the left, we plot the set of all unit vectors as a unit circle. We can denote as U. And in the right figure, we plot the points of AU, which also means that after multiplication, it is observed that A distorts the unit circle, and we can see that it skews space in direction V1 by lambda 1, and skews the space in direction V2 by lambda 2. So it's very interesting. So it means that the property of the the matrix A perform a distortion to the unit circle like this. So the decomposition of a matrix can also tell us many other useful facts about the matrix. But we won't go very deep in this lecture. You can get some in this book or other references. The eigen decomposition is really very useful in many aspects. Here we have another way of decomposing a matrix that is called singular value decomposition. We usually call it SVD. So it's very similar to eigen decomposition, but it's more general. It doesn't require the matrix to be a square matrix, and every real matrix can have a SVD decomposition. So the definition of the SVD is like this. The matrix A can be decomposed to 3 matrices. And if the shape of A is m times n, then the first factor is a matrix with the shape of m times n. And the second matrix is a diagonal matrix D with the shape of m times n. And the last matrix is a matrix with the shape of n times n. It is noted that both U and D are orthogonal matrices. Okay, perhaps the most useful feature of the SVD is that we can use it to partially generalize matrix inversion to non-square matrices. You know that the matrix inversion is not defined for matrices that are not square. So here we have a pseudo inverse. The definition of the pseudo inverse is this. It's very complicated, but we can compute the pseudo inverse in this way. So this pseudo inverse is denoted as A plus. And we can just use the SVD factors of the matrix A to get the pseudo inverse. This pseudo inverse is also called more Penrose pseudo inverse. You know that there are many different definitions of pseudo inverse, and the more Penrose is just the most typical and widely used one. And with this pseudo inverse, we can solve this linear equation system by just do the multiplication between the pseudo inverse of A and the vector B. So this is a very interesting analysis. So if the equation has exactly one solution, this is the same as the inverse. We have studied that if the equation has exactly one solution, it means that the A should be a square matrix, and the columns of A should be linearly independent. So this becomes the same as the matrix inverse. And if there is no solutions for these equations, then these solutions can give us a solution with the smallest error of this L to norm distance. So in the third case, if there are many solutions, this can give us the solution with the smallest norm of X. So this is very, very useful, very, very interesting. But in this chapter, we won't go very deep into the details of the proof of the theory. We just need to get some insight and the concept of the linear algebra. Okay, here we get to the last operation today. It's the trace operator. The trace operator is the sum of all of the diagonal entries of a matrix. It's denoted as the TRA, and it equals to the sum of the elements along the diagonal line. So the trace operator is sometimes pretty useful for us to write very elegant and concise expressions, because it has some very useful properties, like the Frobenius norm of matrix A is just a square root of the trace of A multiply A transpose, and the trace of A is equal to the transpose of the trace of the transpose of A, and also the trace of AB is equal to trace of BA. And it's a pretty interesting and pretty nice operator. Okay, we finally get to the last slide. Here I just list some of the very great resources about linear algebra and matrix series. They are both free and great courses or videos about this field. They are really very great. Okay, today we have covered so many concepts and definitions and theories about linear algebras. They are both very core ideas and relevant to the machine learning and deep learning. Maybe you find some of the concepts very tough to understand, and maybe you are already confused by some of the concepts. If you want to understand better, you can go to check the reference resources listed here. However, I think it's just fine to continue the study of the book with this confusion, because when we go further in this book, we will see how we use the ideas of linear algebras in the machine learning and in deep learning, and in that way it can help us practice the use of linear algebra, and it can also help us to get more insight of the concept we have learned today, and it can help us to understand better of the whole theory of the linear algebra. Okay, here is the end of today's lecture. So thank you very much for your watching. If you have any ideas or suggestions, just feel free to leave your comments and or contact me. If you find my video a little useful, you can subscribe my channel. Again, thank you very much. I appreciate it.